Bom dia a todos. Pô,
Olá, bom dia.
bom dia, bem-vindos aí a mais uma palestra do nosso seminário de Introdução à Engenharia de Som. E hoje nós vamos ter uma palestra do Elias Zea. Como eu disse na última aula, a gente começou a migrar para o oeste. Só estamos dando um pulinho de volta na Europa agora, mas o Elias é originalmente da Venezuela. Ele formou-se em engenharia eletrônica e hoje ele é pesquisador na KTH, né, no Instituto Real de Tecnologia da Suécia. Vai nos contar um pouco mais sobre isso e sobre também o laboratório de acústica e vibração, onde ele conduz as suas pesquisas. E depois vai nos falar sobre o que ele tem feito, como usar aprendizado de máquina para fazer a amostragem de campos sonoros. Elias, thank you very much for accepting our invitation and for taking the time to share your work and also your experience and how to get to acoustics. So we are all very eager to listen to what you have to tell us. Please, our virtual floor is yours.
Thank you very much, Bruno, for this nice introduction. And I could have a guess of some of the words in Portuguese, as I come from Venezuela. So that was very nice. And also, of course, thank you for this opportunity to present my work and to actually share this with your students. I think it's a very nice initiative. All right, so I will start sharing my screen. Maybe I should be careful here. Sharing the audio. Yes, very good. So, right. So today, the topic of today is I tried to frame it in this title. So, what can machine learning tell us about waves in space-time? And my name is Elias. As you can see, I'm a PhD, graduated 2017 at KTH. And this is a work actually in cooperation with Marco Laudato from L'Aquila University. I think he's present also. So I am at KTH, specifically MWL, which is, we're going to go through that in a moment. And I must also, of course, give some credit to the Swedish Research Council, the Vetenskapsrådet, which is financing my research. All right, let's get started. So the outline for today is going to be two parts. The first part, I'm going to talk about my trajectory, a little bit about KTH and the lab, the acoustics lab at KTH, the MWL. And thereafter, I will jump into the part two, which is more the technical part of the talk. And that's going to be in three sub-parts. The first one, the research problem, the methods and results, and then a summary and outlook. Maybe I should try to put the laser pointer. Yes. All right. So I'll start first with part one. So this is a summary of myself. I tried to gather all the information that was interesting to the point where I was born, to the point that I am now. So I'm originally from Caracas. I was born in 1989. And well, I then graduated from electronic engineering, which is, well, in Venezuela, there is no acoustics engineering. So the closest you could think is electronics. That was 2013. And my first time in Sweden at KTH was in 2012. I was an exchange student. So that was during my electronic engineering degree. And I came to Sweden the first time, and well, as you can imagine, it was a very contrasting environment. We are surrounded by the Caribbean, as also most of Brazil is as well. So that was a very dramatic change of weather and climate, of course. But of course, it's also very beautiful on its own. The winter is very cozy, and well, instead of mango trees, we have apple trees. So, okay, one thing for another. And then at MWL, I came back in 2013, actually, and I started a PhD. And this PhD was in sound field separation with microphone arrays. Thereafter, I did a postdoc, which was related to scattering, acoustic scattering in complex enclosures. And after that, I started a researcher as kind of a limbo between postdoc and tenure. So it started in 2020. That was last year. And my topics, as you probably heard from the introduction, but I'll now also say them in English. Topics of interest are acoustic wave propagation and scattering, as well as diffraction. And I am focusing a lot on applied maths, including machine learning and harmonic analysis. And last year, I got an individual starting grant from the Swedish Research Council to undertake 4 years of fundamental research on acoustic diffraction. Maybe I'm going to take this away, actually. All right. All right. So a little bit about KTH. I think it's the best is to start with this short video, and hopefully you can hear it. Let me know if you can't. Yes. So I just realized the Brazilian flag was there in one of the images. That was very nice and unexpected. I didn't know that. So a little bit of
when
facts.
There is samba, there is Brazilian flag, right?
Right. I suppose that's the. So a little bit more about the facts of KTH. So it was founded 1827. It's one of the, well, it's a very, very, very old university here in Sweden. It has 3 campuses today, one of them in the main city of Stockholm, and 2 others a little bit outside of Stockholm. Is a picture on the right. Is a picture, aerial picture of the campus in Stockholm. In total, it's about 13,000 students, 1,700 PhD students, and about 3,600 employees. The education programs they're ranging from natural sciences, engineering science, architecture, industrial management, urban planning, history, and philosophy. And the research is both applied and fundamental, and also covering interdisciplinary and high impact research as well. And some more details. Well, of course, we're very interested in studying climate change and sustainable development, gender equality, future energy supply, urbanization, quality of life, and many other topics. There is a very close connection between KTH, the public and private sectors. And in fact, there is a very close cooperation with many other universities in Europe, US, Australia, Asia, and Africa. You can also check this website if you want to read more. And here are some nice pictures of the archipelago. Well, Stockholm is kind of an archipelago city, so we're surrounded by many, many islands. And this is a picture actually of the midnight sun. When it's midsummer, basically the sun kind of hides for a few minutes and comes out again. So those things are very attractive and very beautiful, of course, scenery and very, very nice landscapes. Now a little bit more into the lab. So our lab, the acoustics lab, is called Marcus Wallenberg Laboratory for Sound and Vibration Research, also known as MWL. And here's a picture of our group. This was taken, I think, 4 years ago or 3 years ago, if I'm not mistaken. And it was founded in 1974 as a donation from Atlas Copco, this very big corporation that makes a lot of tools. And they gave a lot of money to found this unique experimental facility in sound and vibration. And indeed, it turned out to be the largest university center in Scandinavia for sound and vibration research. We have about four full-time professors and around 30 staff, including postdocs and PhD students. And we also have an engineering mechanics program as a track, which is called the MSc, the Masters in Sound and Vibration. And the research activities, we will go a little bit more into detail very soon, but basically spanning the vibroacoustics, flow acoustics, and numerical acoustics as well. And one other thing very interesting is these very unique experimental facilities, as you can see on the right. Of course, we have an anechoic chamber, which is 10 by 10 by 10 meters, cubic meters. We also have a reverberant room where we do, of course, all sorts of tests. And also we have a very nice test rig for instance, muffler evaluations, where the flow actually is silent because it goes all the way through the anechoic chamber and comes back silent. So that's very nice to do some tests in that sense. So more details about the research activities we do. So this is kind of a very nice illustration summarizing all the different activities. We have activities related to aeroacoustics, vibration isolators. We also have activities related to wave-based methods. For instance, here on the left, we see the cabin of a train and the predictions of the sound field. We also have material acoustics, which is also one of the biggest research groups in our lab, dealing with poroelastic media and how to model these anisotropic materials and metamaterials as well. As you can also see, well, most of the applications which lie more on the outside of this ring, so inside you can imagine is more fundamental research, but also in the outside you can see all the applications related to transport and energy industries, which is of course, well, one of the closest connections we have with the industry here in Sweden. All right, so now we can jump into part 2. I have to be careful with the time, so I think we're good. So part 2, so let's get started with the research problem. So the research problem, we're going to start first with the background. So a little bit of background. Let's imagine we're in a room that looks like that. We have 3 sources, for instance, emitting some noises. And we have a bunch of receivers or microphones located in those positions. And we sort of want to understand, or we want to model very well the sound field inside this enclosure. And just to name a few applications of this kind of modeling approaches, well, we have source localization and quantification. We want to understand how much sound power is an individual source contributing to that room. Well, of course, we have noise control if we're interested in controlling different sources in that environment. Sound compensation, auralization, room acoustics. So of course, when it comes to describing and predicting virtually what is going to be the sound in a room that has not been designed. So that's of course an interesting topic. Teleconferencing, and of course augmented reality and virtual reality, where it becomes this kind of immersive acoustics very important. So all these aspects are interesting to these applications. And well, to get very in the very let's say, to get started with this, we have to think always about the sampling rates and the sampling theorem. So Nyquist channel sampling, it requires that the space in between 2 microphones, so we're talking about space now, we're not talking about time, it has to be less than half a wavelength. Otherwise, we're going to basically have some aliasing. And if we look at this formula, then we have that lambda, of course, is going to be the sound speed divided by the frequency. So we have this formula C divided by 2 times the frequency. Spacing between the microphones has to fulfill that, otherwise we have aliasing. And now, to make things a little bit more interesting, I'm going to ask all of you who are in the audience to go into menti.com and put in this code and give an answer to the question of how many sampling points do you think are needed in a cubic meter of air in the audible range. So this is no need to take your calculator, or of course you can do that if you want, but you can also get a guess, and I'll give you a couple of minutes to do that. I'm also going to copy it in the chat. Let's see. This is a direct link to the Menti, so you can also use that.
Is anybody answering?
Yeah, so I see now it's 18 people. I don't want to show it because I don't want to bias the results. Can we see the slides? Yes, of course. I can show it again. So it's around 20 people now voting.
Some people are asking for the code, so you can click directly on the link on the chat.
Yeah, that's perfect. Yeah, using the link is directly going into the Menti.
And I also shared it on YouTube.
Perfect, thanks. Go back to see the results. All right, we have 27 votes. We can wait 30 more seconds. You got to vote. You can also take a guess, and that's equally fine.
That's the test for the discipline, right, Bruno? If anyone gets that wrong, it's automatically failing.
Fails completely.
No pressure.
It's the only test we're gonna do.
I already put mine, but let's see.
Mm-hmm. We'll see. Yeah.
Let's see.
All right, I think for the sake of time, we will have to stop at this point, but I can share the results so far. So 16 of you, the majority, said 13.6 thousand points, then followed by 1.6 million points, and followed there by 1.5 to the power of 10. And then last, the 117 points. So the right answer, after all this suspense, is actually 1.6 million points. 13.6 thousand points is for a square meter of air. But if you take that, well, actually, this amount is for a line. So basically, a meter of air. This is a cubic, a square meter of air, and this is a cubic meter of air. So this was indeed the right answer. So I'm going to stop and share again the presentation. So how to calculate that? You can also just do it for fun. Then M has to be at least C divided by 2 F max, where F max is the highest frequency that we're interested in. And then elevate that to the power of 3 because we're asking cubic meter. You do a square meter, then you put 2 there instead. All right, that was interesting and fun, I hope. But now the question is, actually, this is a ridiculous amount of points. If you think, practically speaking, how many microphone positions we need to use. I mean, 1.6 million microphones or microphone positions of the same microphone. That's just too many points. So the question now is, how can we sample below Nyquist Shannon rates? Is this a possibility, and how do we do that? And this is kind of a summary, a very rough summary of what has been done, state of the art and some trends. And I have divided into 2 different kinds. So model-based, where we use some kind of model approach. And we have the data-driven, where we use some kind of machine learning approach. And I'm not going to go into much detail here, but well, we see, for instance, we have source models, where the idea is to actually model the actual sources in that environment, in that enclosure. We also have wave-based or model approaches, where we're interested in more kind of a field description of this enclosure. A very good example is plane waves or model superpositions. We also have signal transforms, where we actually take your data and transform it into some other domain and try to find a very nice representation of the data in that domain. And for instance, here we have curvelets or shearlets, which are kind of well known in the image processing community. On the right side, we have this data-driven approach. We have convolutional networks. We have this convolutionally sparse frameworks, which work from DTU. The guys at DTU, they presented last year at Internoise, and I suspect in no time will appear at JASA. So very excited to hear that. We also have some units. So these convolutional neural networks that are, well, they are shrinking the dimensions and at the same time concatenating from the decoder to the encoder. And also have generative models, where the idea is basically to learn the description of the data so that then you can generate new data, or you can generate missing data. So we have, for instance, very popular, the generative adversarial networks. This is again by guys at DTU that I think is not published yet, but I know it will be presented at Internoise this year. So also very excited to hear about that. Or variational autoencoders is also another way of doing this. And then we also have unsupervised learning. So unsupervised learning is where you don't have labels, but you're trying to actually understand the nature of the data. What are the structures that are present in the data? And examples of that are dictionary learning. I note here a steady state. So this is work again by the guys at DTU. Presented at the ECA 2019, and because it's steady state, you are fixing the frequency and you're trying to describe that spatial distribution of the sound field with some dictionary learning. And more recently, my work together with Marco, where we have used some kind of dictionary learning, which is called the sparse principal component analysis, but then we use this for data in space-time. The difference here is that we do not assume that the data has to be in steady state, but we actually consider transients as well. And of course, steady state wouldn't work so well for this case. So it's a matter of choosing. And today I want us to focus on these 2 papers. So my earlier work on the shearlet transform, so how to do this with a model-based, and then later we will talk more about unsupervised learning, which is kind of the point of the talk for today, but we sort of need to go through this a little bit very briefly. So basically, there is a research gap, and this research gap is that there is a lack of physics or understanding the physics of what is the diffracted field, what are the diffracted fields in space and time. And of course, this is not new. Pulki and Svensson, particularly Svensson, who I think is present here, he's been studying diffraction for many years, and it is still a very, very difficult problem to solve. To actually, how can one model this decay of the waves? Because originally geometrical acoustics would assume that any reflection will just have a singularity, a reflection, for instance, from a finite edge like this. It will have a singularity, so a jump from the wave value to 0. And of course, that's a limitation of geometrical acoustics. It works for high frequencies, but then in the lower frequency regime, it is not very applicable. In the lower frequency, then you see this kind of behavior, and then it becomes crucial to model this decay. And waves do not become exactly planar or do not become exactly spherical, but they are somewhere in between. And this is kind of the motivation for my work and the work that I'm presenting today, which is related to that. So what happens with transient waves that are reflected from finite surfaces, such as this edge? And this edge also has an impedance that is, for instance, angle dependent or frequency dependent. So these waves that are going to bounce off this edge are going to be localized somehow in space-time. So an example of that looks like this, where this source here is going to bounce from the table, and the microphone that is reading it is going to read the, well, this is a bunch of microphones in the x-axis, and this is the time in the y-axis. And what's going to happen is this very smoothly increasing wave that is going to be the result of this edge of this table. So we're interested in modeling this very complex phenomena that up to this point, well, machine learning can actually do this kind of job, but then we don't really understand what happens with the physics of it. So we kind of lose track of how to model this properly. So now jumping a little bit more into the method and the results. As I said, I had to jump first through a little bit of background before we jump into the actual machine learning part. And this is my paper in JSV in 2019, where I used these shearlets, as I was saying earlier in the table. And the main idea was to model the waves in space-time with shearlets. Shearlets are, they're shapes, elements that looks like this. They look like kind of localized singularities with some extent. They are transient, but they are kind of extended in space and time in this case. And they have different rotations and different wavelengths. So hopefully you can see the last one is very, very thin, and it increases as well. And you can also have translations of these elements. So in some way, what we're saying is that any wave can be a combination of these waves. So in a similar way as Fourier did when he was solving the heat equation and saying that any function can be represented with enough Fourier coefficients. Well, it's kind of a similar story here. We're saying that any wave in space-time should in principle be represented as some combination of these waves. And the problem here, as we stressed earlier, is how to recover these acoustic fields in space-time below the Nyquist rate. So here we have, again, some kind of pressure field in space and time. And these vertical stripes that you see here are missing data. And this missing data, well, we're actually interested in not having to measure that data, because then we will reduce the number of microphones. So how do we actually fill in these gaps? How do we paint through, and how do we interpolate this data? This is kind of the question we're trying to answer in order to get the actual result. So the idea is to use basically these elements and start to fill the gaps in between the missing signals. We take one, we take another one, and so on. And we keep going until the whole data set is filled. And this is an optimization problem that there's no need to go into detail at this point. You can go to these papers and you can read that. But it works in this way, that you're trying to minimize the discrepancy while painting these gaps. So the discrepancy with some kind of meaningful result. And this is some experiments. What happens if we actually do this 80% below Nyquist rates? Meaning that originally we have 100 microphone signals in space. So we have an array, a line array, and we take away 80 microphones and we only use 20 of them. And this is what this looks like in 3 different rooms. And well, this is the original result, which is very smooth and so on. In the middle, we have the result of interpolating whoop, that was a spoiler, interpolating the signals with a low-pass filter, so basically doing an anti-aliasing of the signals, because this is clearly going to be aliased. And well, as you already saw earlier, just now, this is going to result in aliasing. So you see all these different diagonal shapes that are really not physical, and they are not, well, they're artifacts in the reconstructed field. In the third column, we have the result with shearlets. So what happens if we paint these gaps with the shearlet elements? And you see that actually it resembles very nicely the result, even at 80% undersample. So of course, this was very interesting and very exciting results. When I published this, I almost couldn't believe it, but I said, okay, maybe this has some meaning behind, although I still had a lot of doubts. And one of them was that, okay, what about the physics of this? Because shearlets, well, they're not necessarily designed for this kind of data. And indeed, this was one of the main criticisms and many discussions, one of them with Efren Fernandez Grande in the TU, and we had this discussion about the problem of using these elements, which are originally made for image data, but not for space-time data. So what happens in terms of the geometry? So it's a very interesting remark, and actually the way me and Marco, my colleague Marco, who is also part of this work, we got to know each other, because he saw a picture of a cone, and we will soon talk about that too. And he said, okay, but this is a totally different geometry, so you can't just pretend to be using Euclidean geometry in space-time. So of course that was kind of a trick. It works, but it's not really designed for it. So what happens is that space-time is an hyperbolic space, so it's not really an Euclidean space, and there's going to be very fundamental well, implications behind this. So a short geometry detour. So maybe some of you remember this from a very basic geometry. One of the postulates of Euclid's elements is the fifth postulate, the parallel postulate, and basically it says that the sum of interior angles alpha and beta, if it is less than 180 degrees, then such two straight lines should meet at some point. And well, that's basically what this states, and this is essentially true for Euclidean spaces, Euclidean geometries, such as space itself, so X, Y, and Z. But when time is included in the picture, well, basically this violates this postulate. So we no longer have this. And well, it's a lot of different things happen that we don't have to go too much into detail right now. But there is an interesting connection to relativity theory. Of course, no surprise that space-time data will have some implications in terms of relativity. And of course, after contributions from Poincaré, Minkowski, and Einstein, among many others, well, it turns out that some cone should appear in this geometry. And this is indeed how relativity theory, the special relativity theory, came about. Here we see, for instance, the light cone that in some peculiar way is going to show up as well in the acoustics equivalent. So this was one of the remarks that my colleague Marco pointed out. He coming from mathematical physics and relativity theory, he said, well, hold on, you have a cone, you should actually watch out with this. So there's going to be a different treatment of this geometry. And then we started working on this because, of course, why not? And we indeed found out some earlier observations of this kind of geometry. And this is nothing new. Indeed, in the Fourier domain of any space-time pressure field, there's going to be a partition into two cones. So the vertical cone, which is going to be here, is called the far-field cone. And the horizontal cone is called the near-field cone. And what's going to happen here is that, well, of course, the far-field cone is going to contain these propagating waves that basically propagate in space. They do not decay. And the near-field cone, there are waves that are very close to the sources. Maybe some of you have studied it, but they are a bit more tricky to model because they decay with the distance exponentially. And well, they're very important features to use in acousticography and, for instance, vibroacoustics and things like that. But the interesting thing here is that this geometry, this conic geometry, if we take the Fourier transform of this space-time data, we take the 2D Fourier transform, we get the wave number frequency domain. So the wave number is the spatial frequency, and the frequency, the angular frequency, is the temporal frequency, right? And what we see here is going to be intervals of phase velocity. So the data seems to be contained within some intervals of phase velocities. And the phase velocities are relationships between the wave number and the frequency that are linear in this case, these diagonals. And not only that, but we also see some hyperbolic curves here. And this was one of the things that struck me and Marco at the very beginning, that we saw these hyperbolic structures which resemble this relativistic approach. And well, we looked through all the different state-of-the-art approaches to kind of discretize this domain. And of course, we have plane waves, which is a Cartesian discretization of the frequency domain. We have directional bands, which is kind of this discretization. We have shearlets, which is the trick that I used 2 years ago. And then we came up with this a little bit more stranger discretization, where you see that these hyperbolic contours are mixed with these diagonals, which are these phase velocities. And well, this is very preliminary, but this is part of our work in the letter, in the JASA letter we recently published. And the idea is that, well, this Fourier space we should probably model it in this way, because it kind of conforms more nicely with these structures. So, and this is, we didn't really invent this, because this is actually described by Lorentz transformations, which are again related to relativity. So these hyperbolic curves are Lorentz boosts, which are known in relativity, and these diagonals are actually the same diagonals that are used by Pinto and Vetelli, which are going to describe directional bands, telling us different direction of incidence of arrival and the time of arrival of the waves. So there is a very, very strong physics behind it now, so, you know, compared to what I had before with the shearlets. Now, machine learning to the rescue. We finally reached to this point. I hope I'm good in time. I think I'm soon done. So the main idea of this was to use unsupervised learning of space-time data to explore this kind of geometry, to see if this geometry actually comes out of the data. And we take a bunch of inputs, space-time patches of 32 times 32 in space-time, to be specifically about 1,500 of them. We take the 2D Fourier transforms. We take a bunch of spectra. And then we input that to an unsupervised learning algorithm, which is called sparse principal component analysis. You can check more on the letter. No need to go into more details, other than it's going to output a bunch of features. And these features are going to tell us something about the data. In this particular case, we're going to try to represent the data that we're trying to learn with the sum or a combination of these features. Once these features are used, then we fully describe this data set. That's kind of the idea behind this. And these features will also have weights, so then you can combine them and you can recover the field. So these are some of the results of what comes out of these features. So the learned features look like this. And well, there's a couple of things we can see. For instance, this is 18 of them. And we have also overlaid this conic, these hyperbolic and diagonal curves, in order to show that actually the learned components kind of conform to this partitioning, to this discretization, which is very interesting. It was not necessarily the case that it was going to be like that. Another interesting remark is that some of these waves are supported. They're like little blobs. So these blobs have different frequency contents, meaning that there is different wavelengths. They are also localized in diagonals. So for instance, this one is localized in the center. This one is localized on the left diagonal, this one on the right diagonal. And we can see that this element is kind of this element and is also this element. So maybe there is a way to parameterize these components, these features in some clever way. And if that is the case, then, well, some representation that could be done in that sense could be more efficient, or could have more interesting properties. Well, let's see. We also have, well, all of this I have talked in the far field, but it's of course also in the near field. So in the near field, we have, for instance, these kind of structures, and we also have them here. So this one is kind of this one, but it's just shifted within this hyperbolic contour. So all of this actually led us to think that maybe there is a really strong structures behind this kind of data in space-time. And also that these structures are band limited. They are not spreading throughout the whole spectrum, but they're actually very localized. And if that is the case, then any kind of wave should be able to model, we should be able to model it as a superposition of these localized waves. So as a summary, what is the machine telling us? So it's telling us a bunch of things, maybe suggesting a lot of things. So space-time, we need to do it together. So we cannot really separate space and time as we normally have done. But we need to actually glue these two things together. And of course, the description will be more complex, but we can use relativistic theories to actually exploit this mathematics. The learned features are nearly orthogonal, so this is also something you want. You want your features to be orthogonal so that they come with nice properties. They have band-limited spectra, which is, as I just said, is we can model finite waves in space-time. So one of the conundrums in diffraction could be solved by this kind of models. The sparsity of the features, well, because these features are sparse, then we can also reduce the number of samples in space-time, which results less microphone data and cheaper measurements, of course. And ultimately, well, these features suggest a way, it suggests us a way to handcraft a kind of a new Fourier transform that is suited for transient waves that are neither spherical nor planar. This is kind of an example that of how these waves would look like. And just to summarize and give some outlook before the time runs out. So I have today, of course, after introduced KTH and the MVL lab, I have talked about a very specific research problem. So how to model and measure samples in space-time, particularly in complex enclosures where diffraction and this kind of localized waves happen. Then I have also shown how unsupervised learning of space-time data can be applied to these kind of fields measured in real rooms. I have also shown how these learned features are nearly orthogonal, which is very nice mathematically, and how they actually follow trajectories. So these transformations in the spectra that could be modeled with mathematics of special relativity. And of course, future work, which is somehow present work, is to be handcrafting a new Fourier transform that could be applicable for these transient waves in space-time. So I would like to thank you for your attention, and of course, some people to acknowledge. Of course, none of this would have been possible without Marco. I think he's here, so of course, thanks to Marco. And thanks also to Susanne Boy at KTH, and Efren at the DTU, Joachim at KTH Maths, and Ines Lopez Arteaga at Eindhoven, Peter Svensson, who I think is here, Shiva Sander Tavalai, and Kanevren Jarman from Schumberger. And I think the list can go on, but I will stop at this point and thank for all the discussions. This is again research financed by the Swedish Research Council, and well, this is my contact information if you want to reach me. So are there any questions? I think I'm ready to answer now. Thank you very much.
Thank you very much, Elias. Really, really interesting presentation. And Eric and William, are you just clapping or you want to make questions?
Yeah, I think both cases, but
Or go ahead if you have questions.
Okay, Elias, congrats. It's amazing work. It's really, really nice. Congrats for you and all the team, of course. I have, well, let's say 2 questions. How do you see the frequency limits in the time and frequency and space frequency domain? This is one question. Concerning the machine learning stuff, how do you deal with the data to train, extract your results, say that the results are abstract or not? And finally, I was thinking about that if you're dealing with transients, maybe worth looking into the Laplace transform, because you have both solutions at the same time, the transients and the steady state. Because when we are, I was just thinking about when we are doing kind of STFT or spectrograms, we're kind of extending the Fourier transform to transients by using it in chunks of time, for example, or space. But I think this is the reason we use spectrograms, because it's easier to, instead of using Laplace transform. But since you are looking to unknown directions, maybe, if I may say, maybe worth looking into Laplace. So you have this transient together with steady state solutions. And then if you look into how to tweak the transformation, maybe you have something new, or I don't know, just some idea to give to you.
Yeah. Okay. Wow. That's a very interesting. I'm going to start with that point. Actually, I'm going to start with the last question. So I have not thought about that, and I will note that. And yeah, so far we're focusing on some kind of transient representation that, in principle, is possible to extend it to steady state planar waves. So we can show under some conditions that that if you shrink, let's go back here maybe. If you shrink this domain to 0, then you get a plane wave, steady state. So it is possible to show that. We suspect that. But spherical waves that are steady state, that's impossible with this kind of representation. So maybe that could be a possibility. I have, I'm a bit outside of my head right now to think about it, but I will think about that. Thanks for that thought. Then coming back to the first question, so the limit, so the frequency limit for the wave number, maybe we can go to, let's see. Yeah, so we can go here. So normally the distance between the microphones is going to dictate the resolution. No, the sampling rate, the wave number domain. So and the relationship is 2 pi divided by the delta. So it's very similar. It's 2 pi divided by t with the frequency, the temporal frequency. In the case of wave number, it would be 2 pi divided by delta. So a smaller space in between microphones, it would lead to a higher resolution in higher frequencies in the wave number domain. I don't know if that answered the question.
No, I was just wondering about this this colorful pictures you showed us. If you have any considered, I don't know, limits on applying that technique and seeing that results, for example.
So you
for
mean,
the patches, you mean, right?
For the patches?
Yes. Yeah, so this one, yeah. Do you see a limit on that, or is it limitless?
Right. Okay. Yeah. Okay. So in this case, I think, if I'm not mistaken, but I think I need to go back to the letter, but I think it's about 200 radian per meter. In this particular case, we normalize it so that you can see clearly the cone. But yeah, this one is actually 200 something radian per meter, and omega would be the result of 2 pi times 11.25k or something like that, which I don't know what that number is, but something like that. Okay. So there is going to be still a limit, right? Like we cannot escape that limit, and we will have to deal with that when we discretize this transform.
Yeah, in the end, you'll be dealing with, you have a continuous time and space, but you will be discretizing it both in time and both in space. Both in time and space, and you have a limit.
Exactly.
Be it what it is,
yes.
there will be some sort of limit.
Yes, that's right.
If it's going to follow Nyquist or not, you might want to look later for other transforms that might bypass Nyquist.
That's right.
Sparsely promoting or something that I know you've been looking at that already, but there will be a limit. Eric, please go ahead.
Yes, thank you, Bruno, and thanks, Elias, for the presentation. Happy to see you again.
Yes.
So I'm wondering. Also, I read this paper, so congrats to you and Marco as well. I come across it sometimes already, and I think it's actually. So it is easy to come around when you have like a sum of plane waves. Your brain can easily figure that out in space, and time sometimes is not involved because you're taking a state. So I was wondering if you could maybe give more insight into those figures or simple sources. For instance, what would these figures look like if you have piston, or if you have a plane wave, or if you have, like you said, a monopole before, and how this would like in terms of simple sources, so we can get our heads wrapped around it.
Absolutely, yeah. Well, I can try. You know, it's hard without the drawings or the illustrations. But well, first, thanks for a very nice question. So, for instance, just a spherical wave is going to encompass a spherical wavefront, and that is going to basically dictate this omnidirectional propagation in space, right? And after some distance, it's going to decay because it has 1/r decay. So how this would look in space-time is going to look like a kind of an hyperbolic curve, and well, in that case, the corresponding spectrum, in terms of this, for instance, is not going to look is not going to be divided into diagonals, but it's going to be a fully continuous hyperbolic domain. So you still need the hyperbolic intervals, but you don't need the diagonals. The diagonals, they are related to direction of incidence. So if you have a preferred direction of incidence, then you have the diagonals. But a monopole source has no preferred direction, so you have to span all the directions. Then those diagonals disappear. So that's just an example, you know, for instance. The case of plane waves, as I was saying to Will before, is going to be shrinking. And any of these supports is going to shrink to zero. The limit of this support to zero is going to result in a plane wave. And I don't know, maybe I missed your third case.
Like if you have a small piston vibrating and you have directivity.
Right. Then you would probably, yeah, if you have, for instance, a very transient, like you have a hammer impact, and they're going to have maybe a clear directivity related to the structural wave that is going to radiate in that direction. Then you would probably see the direction of arrival in the array equivalently in the diagonal of the spectrum. So you would see concentrated the energy in that along a certain diagonal. If you have the array perfectly in front of the piston, then you would probably see it centered like this. So you see in normal incidence. If the piston is a little bit misaligned, then you would see it maybe a little bit diagonally. So that's also like that.
And I suppose for when you do a Fourier transform of a monopole, you have a singularity. Across the radiation circle, you have that singularity. And how does that would behave in your case? Do you have any comments on that?
Yeah, that's a great question. And well, without going further deep into this maths, because it goes well, we're still doing this right now. But what's going to happen is maybe we can go to this figure. What's going to happen is that well, there is going to be this first hyperbola here, and then there's going to be the counterpart there, and also for the near field, right? And whatever is inside it's going to be the singularity that you're talking about. So in some strange way, well, there is a way to prove this mathematically, but we cannot jump into that right now. It will be a lot of details, but we can show that whatever is inside is actually, we can actually model it mathematically with a monopole, and then whatever is outside, we can model it with some kind of wavelet approach. And what this means is that we can represent both the monopole part of a field and the remaining parts of the field with whatever is outside that. And how this monopole, the singularity, is localized in the spectrum, because that's also a very valid question. It will depend on the rotations, kind of the direction of arrival of this monopole, of the pressure that is emitted by this monopole. So if you have it kind of normal incidence, then you have it very, very highly localized. So this space here is going to be very, very small, and then it decays very fast. Whereas if you have it kind of diagonal to the array, then it's going to expand a little bit more. Then you see it maybe it's going to look a little bit more like this.
I think it applies to the problem we are looking into with the finite samples as well.
Right. Yeah. That's a.
Thanks, Elias.
Yeah. Let's let me go for a question from our that were written in the chat. There's one asking if you could elaborate a bit more on the physical interpretation of these learned features.
That's a very tricky question, but I can try to elaborate the physics of it. Well, there's going to be one thing that I mentioned related to the incidence so the angle of incidence,
which is the
kind of the diagonal support, and another thing is these blobs. So, for instance, this blob here, it means that some of this wave is actually localized within a certain frequency range. And one of the comments that was very interesting from this letter, that one of the conclusions we reached is that, well, if we want to design a transform that has this kind of features, we really need to use individual features. We cannot use combinations of blobs, basically. If we have combinations of blobs, then it's going to be very hard to model individual blobs. So it's better to have individual blobs, and then their combinations are going to lead to different waves. So coming again back to this different blobs of different frequencies, what this means is that you have a wavefront that has a thicker or a narrower wavelength. So it's going to be a faster wave or a more slower wave in time. Because space-time are glued, it's not so straightforward to say that, because you still need to do the same analysis in space. So for instance, this diagonal blob that is there, it's going to be rotated a little bit in space-time. And the wavelength is going to be the wavelength that is combining space and time together. So you cannot really talk about wavelength related to frequency only, but you also need to think of it in terms of the wave number. So in that sense, it's kind of a combined wavelength that is going to be thicker or narrower in that sense. Other than that, I think the far field cone and the near field cone, so how these waves behave in terms of the physics. So one nice thing that it was nice that it came out of the data is that the far field, that's no problem, but the near fields, they are learned in the lower frequency range, and that means that's very physical, because if you're not close to the boundaries or to the sources, you are not expecting any near fields. Let alone near fields in the higher frequencies, because higher frequencies are going to decay faster with the distance. So you would expect, if you expect at all, any near fields are going to be in the lower frequency, because they're going to at least reach to some point of the array.
Cool.
And
okay,
I think that's,
yeah, I think that was clear. One last question then before we close, and that's a more applied question on machine learning. And I was asking which programming language they use for the machine learning algorithm, and if you used any pre-existing toolbox for that, or if you designed the toolbox, and if so, if it's available for the community.
That's a very good question. Well, the language, we have it both in MATLAB and in Python. So it's actually using toolboxes that already exist. And in the case of MATLAB, I think it's called SPASM. The MATLAB toolbox is for sparse statistical regression. And it has one of the components of this toolbox is called sparse PCA or SPCA. And this is what you use in this case for this kind of unsupervised learning approach. In the case of Python, I think it's called scikit under the scikit toolbox, and it's some kind of dictionary learning approach. That was Marco's also contribution. So I think maybe if Marco wants to complement that, you can say exactly the name if you're still there. But yeah, it was so we haven't really derived anything or created any code, but we can share it. I mean, it is nothing strange, nothing particular. What matters is the data, right? So once you have the data, then you can use any kind of toolbox to do this.
Of course. Great. I think those were the questions that came up on the chat. William and Eric also complimented. Seems everybody's happy. We just had a great talk from very interesting subjects, and getting to know that acoustics is closer to physics and relative theory than we thought. So I really want to thank you, Elias, for this great presentation, and hope to see you soon.
Thank you very much, Bruno, and thank all of you for attending and participating. And I think it's a very nice initiative, and I hope the best for the rest of the seminars. And yes, thank you again for the invitation.
Okay, bye-bye. Thank you very much.
Thank you, gracias, bye-bye.
Thank you.
Bye. Gracias.
Bye.
Cool. Just close